So now let's put Dalton's law of partial pressures into action. Here I'm going to do an example where a gas is collected over water. In this example, a 500 cubic centimeter volume of oxygen gas saturated with water vapor was collected at 25 degrees Celsius and a pressure of 760 torr. How many grams of oxygen were collected? To solve this problem, you have to know the vapor pressure of water at that temperature. So the vapor pressure of water at 25 degrees Celsius is 25 torr. So the vapor pressure of water just gives you an idea of the pressure exerted by the H2O molecules that are in the gas phase. So we can use Dalton's law of partial pressures to answer this question. Um, we need to figure out how many grams of oxygen were collected. So that should be a pretty good clue that what you need to go for in this problem is the number of moles of the oxygen. The number of moles of oxygen, of course, is going to be N of O2. And we can get that using the ideal gas law. However, we're dealing with a mixture. We have both oxygen and water in this mixture. So when we think about the total pressure, which they gave us as 760 torr, that total pressure is going to encompass both the pressure exerted by the oxygen as well as the pressure exerted by the water vapor, since those are the two gaseous components here. Oxygen saturated with water vapor. Okay, that's just Dalton's law of partial pressures applied to this problem. So we know the pressure of water, the vapor pressure of water is 24 torr. So we can rearrange this equation to solve for the partial pressure of oxygen. The partial pressure of oxygen is going to be P total minus the vapor pressure of water. So that's going to be 760 torr minus 24 torr. That's the vapor pressure of water. So that gives us a partial pressure of oxygen that's equal to 736 torr. So now we can figure out the number of moles of oxygen by using the ideal gas law, because the pressure times the volume of oxygen, and this is just the pressure of oxygen now that I'm using, because I want to figure out the number of moles of oxygen only. PV equals nRT. And the number of moles of oxygen, if I rearrange the ideal gas law, is going to be equal to the product of the partial pressure of oxygen times the volume of that oxygen over R times T. And we have all of these variables. I need to convert the torr to atmospheres. You guys may remember that 1 atmosphere, the conversion factor is that 1 atmosphere is equal to 760 torr. So that means I can put that 736 torr over 760, and that is going to give me atmospheres. Okay, so let me clean that up a little bit. 736 divided by 760 is going to give me pressure in units of atmospheres. The problem told me that I have 500 cubic centimeters of oxygen gas, and I want to convert the 500 cubic centimeters into liters, because again, I want to match the units of the gas constant. So a centimeter is the same, cubic centimeter is the same thing as a milliliter. And if I want to convert that to liters, it's going to be 500 milliliters or 0.5 liters. So that is what I'm going to put in for my volume. And the reason I wanted liters and atmospheres is because I need these units to match the units of the gas constant, 0.08206 liter atmospheres per mole Kelvin. The last variable that I need to plug in is the temperature. So the problem told me I'm doing this at 25 degrees Celsius. I need to convert that to Kelvin. 25 plus 273 is 298 Kelvin. So if I do all of that, then I find that the number of moles of oxygen is going to be equal to 0.0197 moles of oxygen. The problem is asking me for the number of grams of oxygen, so I simply need to use the molecular weight to convert this number of moles to grams. So let's take that number of moles, 0.0197 moles of oxygen, and multiply it by the molecular weight of oxygen, which is 32 grams per mole. That tells me that I have 0.63 grams of oxygen that are going to be collected over water in this problem. Okay, this is grams of oxygen gas now. Oxygen gas is very light, so that's a fair amount. Okay, now I would like to talk about another application of Dalton's law, which is the concept of mole fraction. Mole fraction is a ratio that we denote with a capital Greek letter chi. Okay, so it looks kind of like this weird cursive X. Capital Greek letter chi refers to mole fraction. It is unitless. It is a unitless ratio. It is a ratio of the number of moles of one component of a mixture to the total number of moles of all components in the mixture. Now, mole fractions can apply to any type of mixture. It doesn't need to be a gas necessarily. But in this chapter, we're just going to talk about mole fractions as they apply to gases. So, for, say, oxygen and air, for example, the number of moles of oxygen over the total number of moles of all of the gases in air would be equal to the mole fraction of oxygen. Okay, so mole fraction is just equal to the number of moles of whatever you're talking about over the total number of moles of every single thing in the mixture. Okay, it's unitless because it's a proportion. And we can also express it in terms of pressure. Okay, so because of Dalton's law of partial pressures, the mole fraction can be expressed not only in terms of moles, but in terms of pressure. I'll show you what I mean with a quick derivation. And this is as long as you have constant temperature and volume for your sample. All right, so why is this? If we think about the number of moles for a gas situation, we can rearrange the ideal gas law to say that the number of moles is PV over RT, right? Now, I can take this definition of N and plug it into my expression for the mole fraction. So let's do that. So the expression for the mole fraction then becomes P1 times V over RT. I'm assuming that temperature and volume are constant for all the components, divided by the sum of P1 times V over RT plus P2 times V over RT plus P3. Okay, I have to go up to however many components I have, so I'll just stop there. You just fill in the rest of the components of the mixture. So again, you get that by just plugging in the definition of N into the expression for the mole fraction based on the number of moles. So now you may notice that you can cancel the V over RT because it's in all of the terms. And that means that this expression boils, and this, sorry, I should put a subscript here. This would pertain to the mole fraction of component 1, whatever that is, because that's what I stuck in the numerator. So if I cancel all of the V's over RT's, which I can do at constant volume and temperature, this simplifies to the mole fraction of component 1 being equal to the partial pressure of component 1 over the total pressure, because the total pressure is going to be the sum of the partial pressures of each individual component in the mixture. So I have two useful expressions for mole fraction. I can express it in terms of partial pressure, or I can express it in terms of the number of moles. And at constant temperature and volume, both of these are going to be useful. So for different problems, you can use different definitions. Let me just give you a simple example. What is the mole fraction of nitrogen in air if the partial pressure of nitrogen is 565 torr and the total air pressure is 755 torr? So in this example, we are given pressures rather than the number of moles. But I know from that quick derivation that I just did that I can get the mole fraction from partial pressure over total pressure. So I can calculate the mole fraction of nitrogen by taking its partial pressure and putting it over the total air pressure, which is 755 here. And that gives me a mole fraction of 0.748 here. Oops, my handwriting is not looking good. 0.748. Now, mole fraction is just that. It's a fraction. It's unitless, and it's always going to be between 0 and 1. So basically, this mole fraction is telling me that air is mostly nitrogen, right? Because mole fraction is always going to be between 0 and 1, and this is about 75 mole percent. So this is how you can put mole fraction into use, bearing in mind Dalton's law of partial pressures.